Oh yeah, we're live, but we can't see anything. Today's stream is a very special stream. Today's stream is all about how to reject the SoyNerd and become the Polymathchad. So, what am I doing today? What do we have going on? I have hardly any room on my desk, but I will try to stream all the same. We have some projects I've been doing for a client. They need some development done with OpenCL, which, if you don't know what OpenCL is, it's a programming language. It's a parallel programming language, which means it's extra hard, more difficult than normal programming languages, because you have to think in parallel about many things happening. And so I was talking to my friend the other day, and he said he doesn't like doing some particular thing because it's too nerdy. He says, "Oh, this is too nerdy for me. I don't like this. I will not do this thing. It is too nerdy. I don't do things with computers. I don't do programming. I don't do any nerdy things like that." And I want to persuade you that, in fact, what you want to reject is the SoyNerd, but not to reject being a polymath intellectual Chad. And this is what we're doing today. We're being a polymath intellectual mega Chad, programming in parallel for a client and making money, which is all mega Chad things to do. So anyway, it's all about the grind. I started this work for a client, and it worked fine when it had a certain size of input data, but then with very large amounts of input data, it doesn't work anymore. And so we have to go back to the drawing board and figure out how to solve this difficult problem. Let's have a look at my kernels. In OpenCL we write kernels, and this one here is a bubble sort kernel. Or you might say bubble sort. That's a soy sort. Any soy dev can write a bubble sort. And you're right, any soy dev could write a bubble sort. But can any soy dev write a parallel bubble sort? This is when the bubble sort becomes much more harder, and you must become polymath intellectual mega Chad in order to succeed in this difficult problem. Let's have a look at my kernel. Let's learn OpenCL. We're learning OpenCL now. I can't see what you can see. What can you see? We're learning OpenCL. Let's see. What do we do? So how does it work? There's this kernel here. It looks like a normal function, but it's not a normal function because it's parallel. Where does it run? It runs on graphics cards. It runs on GPUs, on parallel hardware devices. You might think, oh, my computer's parallel, it has multiple cores. Yes, it does. Maybe it has 4, maybe it has 8, but GPUs, they have hundreds. So we have to think about hundreds of threads in parallel. And what does it do, this bubble sort kernel? Well, it takes some input data here in integer form and a size. There's a size for the data. And this thing could be a power of 2, but it might not be a power of 2. And if it's not a power of 2, that means it's harder, so we have to think more. And then there's some worker flags. What do? Well, they store whether or not the kernel swapped some numbers. Did it do some more sorting? If it swapped some numbers, there might be more sorting to do. So we need to remember if we need to repeat or if we're done. What about this worker stride? That's a new thing. I'm not done with that yet. I just started this because it didn't work. Why didn't it work? Because I launched too many kernels. Why did I launch too many kernels? Because the dataset, the input was too big. It didn't work. It crashed. So we need to think about how we can add something to reduce the number of kernels. So that's what we're doing there. But we're not finished yet. What else do we have? An infinite loop. Oh, infinite loops. Oh, that's hard. I have to think about difficult problem. Oh no. Oh, how awful. I must become polymath mega Chad to be able to cope with infinite loop. But it's not infinite, because you can quit. That's why there's this thing and it says quit. And when quit is 0, we don't quit. But if quit is 1, we do quit. Then there's some other things here. Counter. Counter's a thing. What does it do? It counts. Where does it count? Where is it? Where are you, counter? I can't see. I can't find him. Where is he? Here he is. What does he do? Ah, that's right. It works in 2 stages. This kernel, the idea was, let me show you my algorithm. I'll show you my algorithm. It's on paper. Look. Here it is. Here's my algorithm. Kernel bubble sort. This is the idea. Look at this. Look at this. We take in some numbers. Here, there's 5. And the kernel goes in pairs. And it takes in the numbers in pairs. And it checks them. And if 5 is bigger than 4, it swaps them. And if 3 is bigger than 2, which it is, it swaps them. But if this was a 1 and this was a 2, then it wouldn't swap them. So how does it work? Well, it goes in pairs. And here we have, there will be 2 kernels, and they check pairs of elements in parallel, and they swap them. What about the last one? Well, that's why there's a counter, because if there's an odd number, we should do these 2 first, and then these 2, and then we should check these 2 and these 2. And then what's this? Flags. That's what I was talking about earlier, the flags. They're set to 1 if it swaps something, and they're set to 0 otherwise. And then what do we do at the end? We need to know, should we iterate again, or are we done iterating and we should exit the function? And that's what they're about. And then this is some longer diagram. How does it work? Well, there's some numbers here, and who cares what they are, so I've just written them all as ones, and the kernels go along, and there's this many in parallel. Look, there's 5 for this one in parallel, and they check the numbers in pairs. And then that's right, this is for the flags. Look, this is for the flags. And so when we're done and we've gone through one loop and we've done all the swaps, we have to check the flags. And how do we do this in parallel? Well, it's tricky, but not impossible. Too hard for a soy dev, but it's fine for an intellectual mega chad. And what do? We check the flags in pairs, and if one of them is 1, we save a 1 in the next iteration. And then, well, we've already checked this pair and this pair and this pair, so now let's increase the stride, and let's check this pair and this pair and this pair, and then we repeat again. And now we're on this iteration, and we check this pair, and then there's no pair here, there's just one thing on its own. So we just copy that value. There it is, we've copied it. And then there's one final pair to check. We check this one, and if any of these things were 1, any of them at all, I've written them all as 1, but if any of them are 1, any of the flags are set to 1, we get a 1 at the end. And then there's only one 1 at the end. So only one kernel has to check the 1. And that's what it does. Look, here it is. Where are we? Back where we were. And here's where it does that. So there's this GID thing. That's the index of which kernel we're on. And it checks the flags. And the first iteration, because remember I said if there's a odd number, where are we? Where's it gone? Here it is. If there's an odd number, we have to do this pair and this pair in parallel, and then we have to do this pair and this pair in parallel. So that's what we do. So we need to, for every iteration, it's a 2-step process. We add up, and every time we do that, we increment the counter by 1. And then if the counter was bigger than 2, that means that we did 2 iterations with no swaps, and that means we're done. So we set the 0th element of the flags to -1 to indicate we should quit. And then down here, all the kernels will check, and they'll quit. But the thing that makes this complicated is we have to do synchronization. Otherwise the kernels could run at different speeds, and that would be bad. It would break, it wouldn't work. So we have to have these barriers here. And we have to always think this function is not one function running, it's many, maybe hundreds, all at the same time. So that's why it's difficult, and that's why it's not, you can't do it if you're a soy a soy dev, that's no good. You have to be a mega polymath intellectual Chad. And then there's this thing that flips through the cycles. So there we go. Parallel code in OpenCL. And why you should be a Polymathchad and not a SoyNerd. It's awful working with SoyNerds. You don't want to be a SoyNerd. You want to become Polymath intellectual mega Chad. And my friend is very wrong when he says, "Oh, I don't like computer stuff because it's too nerdy for me." Well, what kind of attitude is that? It doesn't matter what the discipline is. Let's think of some things that are really nerdy. What about IT tech support? Oh yeah, that's nerdy. Oh, I don't think that's very cool. But what if you earn a lot of money doing IT tech support? Oh, lots of money. That's pretty cool. So it doesn't really matter what you do. It just matters that you're good and you make lots of money. So my friend is very wrong, and you should reject this attitude. You should not reject to learn something just because you don't think it's very, very cool, because this is not a cool attitude to have. What is cool is to become the Polymathchad of your specific area and to be able to earn some big dollars doing this. Many people can do code. Many people do C++ code, C code. I do this as well. But when my client comes to me and says, I need parallel code, I need code in OpenCL, well, how many people are there out on the internet that do C, C++? There's millions of those people. How many people do Polymathchad parallel programming with OpenCL? Not very many. So it's a niche market. You tap into a niche market. Doesn't matter if you think, oh, it's not very cool because it involves computers and that's nerdy. It doesn't matter. Don't be a soy nerd about it. Don't be one of these beta male soy nerd. I never leave my house. I never go in the sun. I never lift. I do no exercise. I always complain about everything. Oh, I report people to HR daily. Don't be one of those people. That's a soy nerd. It's not cool to be a soy nerd, but it is cool to be a Polymathchad. So become Polymathchad and learn hard things. Learn difficult things. Grind every day, grind and learn a hard thing, a difficult thing. And then you will become Polymathchad. And this is the message of my stream. And you must learn this message. You must write down this message. And you must every day say to yourself, reject SoyNerd. Become Polymath.